This talk is titled Impressions of a Unified Standard Model Mathematica Notebook and T-shirt. It was given at the 13th Eastern Gravity Meeting in May of 2010 in Raleigh, North Carolina. And this meeting is really geared for graduate students in various forms of gravity research, folks who study things like gravity waves and do a lot of computer modeling of things to get their feet wet, as it were, presenting their ideas to a public audience. And they're kind enough to let folks who aren't really officially connected to anybody to give their own talks on this sort of technical nature. So the way I started it was to say, well, I actually had worn this t-shirt for 2 days. It was a different t-shirt, honest. And not many people had walked up and looked at it up close and personal. Why? I don't know. But it says, the stand-up physicist said, and you have this field equation which looks just like the Maxwell equations in the Lorentz gauge, except that it doesn't have any of the gauge terms. And the current is actually zero also, which is kind of interesting. And there was light, gravity, radiation, and a nucleus, but no stinking Higgs. On the back it says, one Lagrangian to rule them all, J.R.R. Albert Tolkien, and then the Lagrangian actually using symbols that are kind of novel, but there is a key to explain it. It says the box square sort of thing indicates this hyper-complex product, and when things are just multiplied, it's the quaternion product, and there are actually no Greek letters in here. There's no tensor algebra going on, so that's kind of intriguing. The Stand-Up Physicist Project is an outreach program via YouTube. The shows like this very one you're listening to are very technical. There is lots of math, even by MIT standards. The running time goes anywhere from 20 minutes to an hour, and I can do that because I'm a director at YouTube. And it has usually a 3-minute epilogue, a little comedy shtick. These ones that are actually redos of talks I do, unfortunately, I don't have the little comedy stuff for you. I say that I usually provide that as a reward for sitting through so much nerdly stuff. And this way I'm actually able to reach large numbers of folks. There have been 110,000 views. In this lecture hall where this actually happened, there were possibly 40 to 50 folks. The folks who read it, to watch it, are what I call semi-skilled, in the sense that, yes, they have done a little bit of this, a little bit of that, or in the math world, in the engineering world, or maybe they haven't. That's okay. I want to show them what the real stuff is like. And the reason I brought this up was because that someone in this technical audience might actually hear from them one day. Because if some undergrad says, well, I was thinking about the derivation of the Maxwell equations from the Lagrangian, they would say, oh, where'd you learn that? And I might be to blame for that, and I think that's kind of cool. It's kind of also cool that we're reaching folks all across the United States and all across the planet, actually. And I've seen recently an uptick in the amount of interest, which I attribute partially to my kind of material claim that my theory at least can fit on a t-shirt. So there are 4 steps to understanding this particular t-shirt. You have to understand what quaternion hypercomplex products are, that gauges cancel, so there's no need for the Higgs boson, that there's symmetries and charges of all known forces, and yet you derive the field equations on the front by you applying Euler-Lagrange. And that is really too much to do in the allotted time, which was 12 minutes. And I should say, I hit that time point in the talk. I'm not going to do that here. I'm going to be a little bit more relaxed and not as compulsive about hitting the 12-point time point. I'm not going to add any more slides, but maybe I'll slow down. So this is the visual steps to understanding the content of the t-shirt. So we want to understand light. And light is based in the physics kind of sense on a symmetry known as U1 that has a representation which is a complex number normalized to itself. So it ends up being a unit circle in the complex plane. Well, I'm using quaternions here, and quaternions can be viewed as three complex numbers that share the same real. And you see an A over a norm of A, oh, that has U1 symmetry, as does the B thing. And that phi is in every single term in that Lagrangian, and therefore I will have U1 symmetry. And where you have U1 symmetry, you end up having a conserved charge. And since there's only one element in the Lie algebra, that's a fancy way of saying it only depends on one number, there's going to be just one conserved charge. That charge is none other than the electric charge. So we can spot how light is present there. For radiation, I'm referring to beta decay, the weak force, and the symmetry is known as SU2, and it is also called the unit quaternion, so oddly enough, I can do that with quaternions. And a common way of doing that is take the exponential of one quaternion minus its conjugate. That basically wipes out the scalar, leaving you with 3 left over, and that is consistent with needing a Lie algebra which has 3 generators in it. And there are 3 conserved charges. There is a perfect lineup like that. And since this isn't phi, the phi is everywhere, this Lagrangian is going to be able to have that symmetry in there. It's going to conserve those 3 charges. And since I have U1 sitting right next to SU2, I have electroweak symmetry, which is nice. But if I want to get out to the nucleus, I need SU3 symmetry. And that has 8 elements, so I thought I'd just take one electroweak symmetry, multiply it by another. But if you know your group theory, you'll know you'll just get a third element of of electroweak symmetry. So there's an absolutely critical little star in there. So now this has a different multiplication table than electroweak symmetry does. And it depends on 8 things, and it definitely has a normal one. So this sounds to me like a way to represent the group SU3. It is certainly not... I don't know if anybody else uses it. I do. But what's so cool is it is a very compact way of writing the 3 symmetries that we know appear in the standard model. In fact, it's the opposite direction of the way most folks go. In fact, there was a lot of excitement a little while ago when this monster group or something was shown to have all these kinds of symmetries in it. And I'm not making something huge. I'm actually making it smaller, which is nearly impossible to do. So then I claim there's no stinking Higgs. Well, why do I make that claim? It's because that minus del phi del term I'm thinking is going to be doing light-like work, but it is gauge dependent. Therefore, it does light-like work for things that have a mass. And the line above it, the plus thing, that is also going to be gauge dependent, but hopefully doing the work of gravity. But since one's a plus and one's a minus, those gauge terms cancel, so that gravity and photon can be gravity and electromagnetism can be mediated by a massless particle such as a photon or graviton. So I do this magic trick of having these two fields that depend on mass, and yet the mediating particles have zero mass. But I do that without using the Higgs mechanism. So there's a $10 billion experiment going on at the Large Hadron Collider, LHC, and I'm saying, well, this t-shirt, I'll put this t-shirt up against your $10 billion collider and see who wins. Now, if you want to get to the field equations on the front, you apply the Euler-Lagrange equations to the Lagrangians on the back. And then I say the stuff with gravity has to do with using this hypercomplex product, which only raises the question, what is a hypercomplex product? Well, first let's start with quaternion products, because they are a mashup of scalars and vectors and complex numbers. And I would argue that anybody with technical experience has been using them since high school, if not even junior high. It involves a real scalar and a 3-vector, which is actually imaginary. You just put them together and it makes a quaternion. Now think of all the possibilities if you have 2 scalar 3 vectors next to each other and you want to just multiply them out. What could you do? Well, you could just multiply the scalars together and you could take the dot product of those 2 vectors. Now it's got the minus sign there, and that's the complex number flavor sort of thing, because if these are thought of as imaginary v and imaginary v prime, and I form my dot product, then I've got the imaginary numbers squared. That brings in the minus sign, and that's really all there is to it. Then either vector can be lengthened or shortened by the scalar, and you get the cross product, and that's it. What's different is that I always do all of these things. I think that to make things simpler, people do just one thing. They'll just focus on, say, the cross product, and they'll ignore all the other things that could be going on. And I think this nature works by always keeping track of everything, and I think this kind of is a step that direction. So hypercomplex products, in contrast, are simply commuting quaternions. They're quaternions with absolutely no minus signs. I call this the California representation, all sunshine, all positive. And the problem with doing that is, how do you indicate when you write it down to somebody? I mean, look, I'm just writing these things right next to each other, just like I did for the quaternions. And so my idea was to put in this box square thing. So this is something that I do, and I don't think anybody else does, but I hope it helps makes things clearer that both of those 4 vectors are the same as the 4 vectors for quaternions. It's just when I decide to multiply them, I'm going to use this box square thing. Everything's going to be positive. Well, that creates a problem for the cross product, which you have to work at really hard to remember which one is minus, which one is positive. And this time you don't have to do that. You just say it's the circle X thing. It's the symmetric curl is actually how I refer to it. It's got a symmetric curl, so I know what all the signs are. They're all the same. They're all positive. I can remember that. Unfortunately, they're too positive. So you had to bring in some minus signs to make this relevant to physics in my experience. And that is you need to use a conjugate operator to throw in that negativity and end up with exactly the same scalar. The reason that scalar is so important is that's known as being Lorentz invariant. So hypercomplex products combined with one conjugate operator will give you a Lorentz invariant scalar. The 3-vector is Lorentz covariant. We know how it changes. Okay, so now we're going to form quaternion products from a differential operator and a 4 potential. And what's amazing is those are the electromagnetic fields. So you basically are going to get div grad, curl, and 2 time derivatives. And what you really get out of this is every conceivable way that a 4 potential can change in 4 dimensions. This is the complete story. And I find that very satisfying, but what's even better than that is the fact that that is how we define the E field. We define the E field as minus dA dt minus grad phi. And we define the B field in electromagnetic theory as the curl of A. And I'm like getting these things using the most basic kind of operation I could conceivably come up with. Now, there's a third player in this game. You see this del phi dt minus del dot A. I'm calling that G short for gauge. This is a gauge field. And in some ways I'm rewriting something that's really well known. This is basically exactly the covariant derivative of a 4 vector. So del mu a mu gives you all of these exact same terms. But with quaternions, I don't have to remember to write my indices up or down or any of that stuff. So now I repeat the exercise, but with the hypercomplex product of a differential and a potential. And I think these fields are related to gravity. And you see all the same terms. You don't see all the same signs. Well, actually, you do for the first one. The first one is exactly the same. The gauge term is the same. But there's one sign flip going on with the dA dt. And the key part in the the B-like term is that it's the symmetric curl. All right, so how am I going to use this? Well, on the t-shirt, we have the different squared fields wipe each other out. And that's why there's really no need for the Higgs. So, how do I explain this? When you switch the order of the potential and the del, the only thing that switches its sign is the B field. So it goes back to high school algebra, where if you had b squared minus e squared, you go factor that. That's got to be b plus e, b minus e sort of thing. There's an additional twist in this exercise just because those are like imaginary numbers. When you multiply them together, they go into the scalar with one more minus sign. And you do a darn similar exercise with the symmetric with the hypercomplex product, and that's all well and good. Oh, and that's actually kind of interesting that when you look at that, we had to put the conjugate operator on both sides to kind of proceed. All right, so in these next few slides, I actually crank through doing the squares. And there are all these terms, and I originally thought this would be really scary, but squaring things makes things so much easier, because you just say, what is everything there? I just square it, and then I figure out what the cross terms are, and then if the signs are the same, then the cross terms will have the same sign. If the signs are different, the cross terms will have the opposite sign. So that those two lines are the E field, the big E field squared, and the same darn logic goes into figuring out the B field squared, where you don't actually have to keep track of where a dAx dy comes from. It can be hard to remember that sort of thing, but you don't have to. You just say, I'm going to use every single one of the ones out there. Well, actually there's 6 of them. So you just come up with the 6 of them, and you just know they're going to be squared. And then you have to figure out which ones are going to be the cross terms, and that they flip signs because they've got opposite signs in the cross product. So that's all there is to that one. So now I'm going to repeat the exercise for the fields that are related to gravity. And you go, wow, that was very similar. Let me go backwards. Okay, so the only thing that changed signs were the cross terms, the things with 2's in them. That's kind of nice. So if I combine the two, look, they go away. How nice! That's sweet. And that's what's on the back of the t-shirt. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 terms there on the back. And it turns out there are 12 terms on the front. And they use good old Euler-Lagrange to make that transition from the back to the front. So I used Mathematica, a symbolic math program, to confirm that the math was done correctly. The story is that I wrote a 27-page technical paper, and I submitted it to several journals. And the first journal, it was Classical and Quantum Gravity, considered it too radical because I used quaternions, which most people actually about half of the folks have maybe heard of, but they certainly don't work with them. And hyper-complex numbers, which really, really few people have ever heard of. And so they suggested I send it to the Foundations of Physics, because they are into more radical concepts, more edgy. And they wrote back to say, well, actually, that's really too conservative. You're using Euler-Lagrange, that's so 1800s. Their other criticism was that I wasn't referring to the modern literature. What paper specifically was the inspiration for all this work? And what am I going to say? Well, there was nothing. Well, that's accurate, but apparently was the wrong answer. So what I did after receiving those thumbs down was I ported all the words and equations into a Mathematica notebook, and so that every single expression could be confirmed to be correct, at least symbolically. And in the process of doing that, I actually showed that one of my terms was wrong. I forgot a conjugate operator, so I added that, and things were better because of it. So this is all available at online at that email, that bit.ly address. It is case sensitive. But it's not going to be on the preprint server because I can't put anything on the preprint server. I don't come from an appropriate institution. My basement is not looked at highly by officials. Now, the comments and critiques that I've gotten from Eastern Gravity meetings in the past have actually been quite useful. At the 7th meeting, which was at Bowdoin College, I think that's up in Maine, someone from Florida said, hey, you should calculate the precession of the perihelion of Mercury with your proposed metric. It's the exponential metric. And I said, that's absolutely solid question. I said, I don't think I really have to do it because I'm the same at first order ppn accuracy, so therefore it's going to turn out the same. Well, that's true. I mean, that is a valid way to reply, but it's kind of a wimpy, avoid the issue sort of thing. So I kept that in the back of my mind. I got to do this, but I've got limited skills. So it took me like literally 3 years before I found somebody who explained it simple enough so that I could actually do the derivation, do the calculation. And yes, my metric actually worked perfectly fine. So that task is done. At the Wake Forest meeting, Eastern Gravity Meeting 8, Clifford Will was, who is a leading expert on experimental tests of general relativity, gave the keynote. And I asked the very first question of the conference. For light bending around the sun, there is something called parameterized post-Newtonian accuracy. It is a pretty darn sophisticated way of saying, well, we're stepping away from Newton. And as we step away, in that first step away, there are like 10 parameters out there. And depending on what sort of theory you have, you make certain claims about the values of those 10 terms. For general relativity, most of them are 0. They're either 1 or 0. It's kind of like, for other fancier theories, there are other quantities that are not 0. And most of those things that are different from general relativity, the Minkowski metric, have been just shown to be wrong. But my metric, because it's coming out of a theory that I think you can say is even simpler than general relativity in a technical sense, it has exactly the same first order ppn coefficients as general relativity. But if you go to second order ppn accuracy, it makes predictions that are different, specifically for light bending around the sun. It predicts, my work predicts more bending. So this is kind of like 1919 2 second round. Okay, in the first round in 1919, at a 1.5 arc seconds is what general relativity predicted, and it knocked out Newton's work, which predicted 1.75. Now, people looking back at the data think that maybe the game was a little rigged. It wasn't until maybe the 70s when real data for light bending got to that kind of real confidence level. But they've really moved beyond that. They've got it using radio telescopes. They've been that down. They've improved it like 10,000 fold. So general relativity, or I should say the coefficients that one uses, have to be consistent with the general relativity ones to first order ppn accuracy. And then it's, well, where's the second order ppn accuracy terms? With a metric, you can just kind of crank it out and find out what those are. And my proposal it predicts like 12% more bending. So I asked Will in that first question, I said, when are you going to push the experimentalists out to that level of fidelity or accuracy, whichever though is the right word? And he said, there are no plans to do that. It's like, damn. I did a follow-up. I said, even in like committee meetings, when the people are just shooting the shit, And he said, oh, I think that came up once. This is like a millionfold more sensitive. I mean, literally a million more fold more sensitive than the 1919 measurement, and it's can be drowned out by so many things like the sun spinning and a quadrupole moment. So that's a bummer. Well, at the Eastern Gravity Meeting number 9 at MIT, number 9, I showed how the Christoffel symbols could be used to constrain the G00 term of my metric, and somebody there said, well, what about the other terms? It's like, oh, that's a perfectly valid question I don't know the answer to. And it was only earlier in this year, I think, when I was writing that paper, that I came up with a way to do that, and I got that all confirmed in Mathematica, so I feel pretty good about that. And at the Eastern Gravity Meeting number 10 at Cornell, this fellow, Ed Milch, he is a fellow who, in the 50s, as an undergraduate, noticed an inconsistency between how one treats a scalar field theory like gravity and how one treats a scalar field theory like electromagnetism. And at the Cornell meeting, it was packed because it was also a celebration of a famous physicist. And so folks like me, they said, why don't you guys just not talk? This was like 2 days before. Just go and present your posters, and probably no one will show up, which is actually what happened. Like, really nobody showed up except other people giving posters. So I decided that I would go and spend quality time with such folks and find out what my if I had a technical complaint or issue, or what that was. And so with Ed's work, he said, hey, I think we can resolve this by using negative mass. And I said, that's going to be a hard sell. So I decided to investigate a little further, and what was so cool was I found out that none other than James Clerk Maxwell himself complained about exactly the same issue. So Ed was onto something. But Maxwell's solution was different than Ed's. What Maxwell realized was, just by calculus, what you do with these things is the first thing you do is you take a derivative of that potential. So you can add an enormous constant. So if you add an enormous constant, then there's no problem with this being a minus sign for gravity. But Max was good. he could find no reason to just tack one on. And I consider this to be one of the great predictions in field theory done by Maxwell, because in 1915 Einstein came up with his field equations for gravity, general relativity, and he thought it was so hard to solve that it might not happen in his lifetime, but actually was done like within a year by Schwarzschild before he died on the battlefield. And the solution that Schwarzschild came up with has this G00 term that has this big honking 1 minus 2gm over c squared r. And I call it big honking 1 not just because it's one, it kind of compared to the term, because the G is got 10 to the minus 17, and that c squared is in the denominator, and you're putting like 10 to the 8th squared, so 10 to the 16th down there. So yeah, you can have a big mass, but you're flooded by all those other signs there. R's are usually pretty big too, making that term really weeny, okay? And so if that term is really weeny, then that thing is always going to be positive, and you don't have to throw in a minus mass to make that thing positive and therefore consistent with EM field theory. So I know that virtually every single undergrad or high school book out there will say that, we're going to use this potential and we're just going to have it be the mass over R. And I'm going to stick with Ed, and actually more importantly, Maxwell, and say, no, every time you write that, it's wrong. And this is the kind of harsh-ass kind of way physicists can be. I've got to say, you got to have that big honking positive constant out there, or you cannot tell a consistent field theory story for gravity and electromagnetism ever. Okay, if you want to just cut that corner, then this fellow is been saying this story since the mid 50s, and nobody's come along to say, well, you actually have a kernel of truth. That is, it's bad to just say it's wrong. It's just wrong to say mass over R. You've got to say big honking constant minus mass over R. That's the way you make the story consistent. And so I'll be consistent with that until I reach old age, and that's the way it goes. And then I said critiques certainly are welcome. They certainly are welcome off the comment sheets of YouTube, or you can look up my email address easily enough. I don't hide it anywhere. And as I finished it with, now you can wear more than anyone else in physics knows today. And you can even buy the t-shirt, which is fun, because if you're just walking around a parking lot at the Stop and Shop like I was today, occasionally people will stop and go, whoa, what was that? And maybe you can't explain it, but at least, I don't know, I think it makes it much more concrete and much more fun. So thank you. Oh, actually, let me say this. I did get some questions. 2 questions, actually. One was to point out that what I have done here is I get these field equations, and they are really kind of similar to what's known as the linearized form of Einstein's general relativity. And that's what I kind of spent a lot of time thinking about at the conference. And I decided that, sure, there is a lot of overlap between my work and the linearized equations of general relativity. But there are concrete reasons why we know the linearized field theory, useful as it happens to be, cannot be correct in the long run. It's because it's an exact copy of the field equations of Maxwell, of electromagnetism. I mean, it only works by having 2 charges. That's not really gravity. Okay, that sounds like a lousy approximation, but it's a useful approximation. And essentially what I've done is done a variation on the linearized field equations. Now that variation does not lead to equations that are the same. As a matter of fact, all the terms turn out to be the same. What is different is that there are a few critical sign differences. For example, they had in the linearized equations, they have a curl, okay, with that sign flipping going on. Well, I flip half the signs in the curl thing so that I get a symmetric curl. And a similar kind of half the terms flip sign, I think, probably for the E-like field. So it really has a lot of symmetries, a lot of similarities to the linear field equations, and I just, in essence, am putting in what I think are absolutely vital sign changes, but I'm not putting them in by hand at all, because I've got the Lagrangian, and when you go through the Lagrangian itself, that's how you see what those sign changes are. And then somebody else said, well, if your metric really is different, you're going to affect how we describe neutron stars. And I had to nod along and say, yeah, that is exactly true. I don't know how a neutron star works. I told her, I said, thank you very much for that question. I'm going to think about that for years, because that's the way I am. But I will see if anybody has introductory level descriptions of neutron stars and see if I can get anywhere in that topic. But it is my responsibility to give it a try, so I will. So anyway, that was the story from North Carolina, Raleigh, and I hope you enjoyed this little lecture. Thank you very much.